Okay, so welcome to lecture 24. Today we're going to start applying some of the things we know about the Sturm-Liouville problem, as well as what we know about the different coordinate systems to solve the problem of separation of variables, or sorry, the wave equation on a disk using separation of variables. And it'll also give us a lot of insight into how the wave equation behaves in general on general shapes. So the first thing, once I can start moving, let's just write down the equation that we're solving. The one thing I must say, this in Follow lecture 20, he does the same problem, but with a slightly different approach. You can actually look at this, and if anything I say is unclear, you can look at the way he does it. I'm going to try and be slightly more complete in the sense that I'm going to tell you how many of the results that he just gave are derived. And I'm not sure if I'm actually going to finish this lecture today and then maybe carry it on next time, or well, we'll see. Because I want to go reasonably slowly. So we have the wave equation. I'm going to define delta to just be the Laplace operator. So it's just the first derivative with respect to x, 1, and the double derivative with respect to x2. And then we have our wave equation, which is just Laplace of psi minus 1 over c squared psi tt. And we want to solve that thing on a disk. And the way we go about it is we separate the spatial and time variables, like we've done when we did in the general, looking at the various problems that we could separate in, I think, lecture 21. And the way we do that is we firstly make an ansatz that the solution can be written in this form: f of t, a function of t times a function of x1, x2. And this is a safe ansatz to make if the equation is linear, which it is in this case. It is not, you can't generally make that ansatz and it'll work. So what people do for most parts is they make it and they try it, and if it works, because the solutions, we've proven that the solutions to the wave equation are unique, then we're fine, we've got the answer. So what we do is we basically substitute this thing in there, and then the Laplace operator acts only on the spatial parts, only on phi, and the time derivatives act only on f, and then we divide the whole equation by f phi. Okay, so this we've done before, and what we get is basically the Laplace applied to psi divided by, which is just the Laplace of f times the Laplace applied to phi, divided by f phi, so we're left with Laplace of phi divided by phi. And I'm going to move this thing to the right-hand side. The second derivative with respect to t applied to psi is just f double prime times phi, but we're dividing by f phi, so phi's cancel, and we're left with f of t. And then clearly this is two equations of different independent variables, and that can only be true if both equations are equals to the same constant. That constant we're going to call k. Okay, and that's our separation constant. And so the one where we've only got one derivative, or the second derivative with respect to t equals to k, we can now solve, because it's just a harmonic equation that we've done often, and we have that omega is just c times, which is the speed of the wave on the membrane, times this separation constant k squared. And the general solution to this thing is you have your two independent solutions. It's basically ak cos omega t plus bk sin omega t. Okay, so we solved the time part, and we did that previously as well. What we're going to do today is look at the second part over here, which is Helmholtz's equation. Okay, and the domain of integration we're going to do is on the circle. So we're going to have a circle with radius 1. Here's our x1 and our x2 coordinates. And we're going to try and do it using so this is what's different from the lecture notes from Follow. We're going to try and use it using or do it using the technology I told you about, all the different coordinate systems. So, and just one more comment, the thing I did last year is I actually tried to solve this thing on an ellipse. And you can do the separation of variables there as well. I'll include those notes if you're interested at the end of the slides for today. So you can see the first part of that is actually easy and a very good example of separation of variables. Where I ran into trouble last year was actually finding the solutions to the Sturmoville problem is not so easy. But I can add that part too and upload the lectures. So if you really want an intense experience, you can go and look at that, but it's not required. But what is interesting, however, is to see how when you go from the circle to the ellipse, what changes and what the structure changes like. Okay, so the second equation that we're solving here is just the Helmholtz equation. So here we have it. And we want the solutions on this domain. So x1 squared plus x2 squared is less than r1 squared. And what we now do is we want to seek coordinates that is fitted to the boundary so that we can implement the boundary conditions easily. And also so that it's easy to specify the initial conditions. But in addition, we want coordinates that we can actually solve the equation in analytically. And to get that, we have to find coordinates in which this equation is separable. And we know from 2 lectures ago that unlike randomly guessing like I did for most of my life, there is actually a means of finding a list of all the coordinates that you can explore, and so you can do that. Okay. And in particular, if you remember from lecture, I think 20, we found that there was one set of a coordinate transformation that would actually take you from x1, x2, where you want to circle, onto a c1, a c2 that was your polar coordinates, and that's the right one to choose. If, for example, your circle was not at the origin but shifted up to say over that point, then you would use a combination of the coordinate transformation I'm going to have now plus that additional coordinate transformation that actually shifts the origin. So you'd basically use 2 transformations. Okay, so we now want to find the coordinates that it is separable for analytic solution. And as we looked in lecture 21, the approach we take is z is equals to, we write it in the complex domain and we make an analytic transformation. So we have z equals to x1 plus I x2. We have the coordinate we're transforming to, w equals to c1 plus I c2. And we found that if we do the coformal transformation that looks like this, so the function z is now a function of w, an analytic function of w, and its real and imaginary components you can compute from there. And we found that if the analytic function we choose to be e to the w, then we're actually going to transform the thing onto a circle. And you can see that because this thing, simply if you write out the real and imaginary parts of z, you get it's e to the c1 cos of xc2 and e to the xc1 sine of xc2. And if you put c2 equals to phi and e to the c1 equals to r, then you have exactly the polar coordinates. Okay, so it fits into the framework of looking for separable coordinate systems for the Helmholtz equation that we did last time. And the boundaries, that's the only thing that's sometimes tricky. And in this case, in this example, it's easy. It became harder in the elliptical example. But the boundaries we have is basically we want to make sure that these coordinates cover this whole circle. And so we know e to the c1 must go from 0 to r1. So we have that e to the c1 is 0 if c1 is minus infinity. And if c1 is ln of r1, then e to the c1 is just r1. So we have the boundary on the c variable, and the c2 variable is an angular variable, and so it must go from 0 to 2 pi. Okay. And these things, these limits are important to get, but you can get them by simply looking at the domain that you're integrating over. Okay, so that's our new set of variables. So now the next step is we want to transform the Helmholtz equation into these variables. And we did that in general in the, I think it's lecture 21. And the way we do it is we have the analytic transformation, but in order to transform it, you had to take derivatives with respect to z and z bar. And so to take those derivatives, you needed the derivative of the transformation, okay? And that thing I called G prime in the previous notes, which is just dz dw. So in this case, it's simply e to the w. And the other thing that we also had is we wanted the norm squared of this transformation. And in this case, which we proved the last time would be separable, and just to check that it is, we have G prime squared equals e to the w plus w bar. And that, in fact, has to be real, and it's just e to the 2c1. So effectively, if you're writing this in polar coordinates, it's just r squared. Okay, so that's and it's separable because it only depends on one of the coordinates. Okay, so now we're in a position just to rewrite the things in the c1 and c2 coordinates, and I did that in detail in lecture 21. I'm not doing it again. But we basically derived that in the new coordinates, the differential equation looked like this. And so for our particular example, that is just minus k squared, which is our separation constant, e to the 2c times phi. Okay. And the great thing is that this equation is actually separable. And the way we're going to go about it is simply to make the separation ansatz, and we're going to say phi of c1 and c2 is just the product of two functions of the independent variables independently. So we have p1 of c1 and p2 of c2, and we substitute this ansatz into equation 2, and what we get, and we're going to divide, just as we did in the case for the time variable, by p1 and p2, and what we're going to get is this. Okay, so here is the second derivative with respect to c1 of phi, which just is the second derivative of this function, times p2, and then you divide the whole thing by p1, p2, so p2 cancels, and you've left with this first term over here. The second term here is the second derivative of c2 applied to phi, and when you assume this ansatz, then it's just simply the second derivative of p2 c2 times p1, and you're dividing by p1 p2, so you just get this term. And then this last factor, I've just moved it to the left-hand side, and I'm effectively dividing by phi equals to p1 p2, and so we're left with this thing. And so here you can see that, in fact, we have, this is dependent only of xc1, this part is dependent only on xc2, and this part is dependent on, this part is dependent on c1, this part is dependent on c1, and this part is only dependent on the independent variable c2. So there we're going to make our second separation. So let's just write that out. Okay, so the separation ansatz lets the Hamilton-Jacobi equation decouple, the Helmholtz equation decouple. Here's the thing that we had on the previous slide at the end, and what we're now going to do is introduce a separation constant and let the things that depend on the different variables independently be equal to the separation constant. And so we now get two equations. The first thing is those that depend on c1, so it's this p1 over p1 double derivative over p1, and it's this part over here, and we're going to put that equals to beta, and then we're going to have the second equation, which we basically move this thing to the right-hand side, and we're going to put that equals, so we're going to have a minus, and that's also going to be equals to beta, so we have this thing equals to minus beta. Okay, so we've now taken our Helmholtz equation, and we've reduced it by the separation ansatz into two separate ordinary differential equations. Questions at this point? Okay, so now once we have that, we can write down the full solution So the wave equation, and I'm going to basically represent it abstractly like this, we haven't yet told you anything about the separation constants k and b. Okay, that's going to come as we solve these two equations. But I just want to give you a schematic feel for what we have. Is we have some function that's dependent on k, f, and in fact, I'm not going to wait. Okay, we have f of t that is dependent on k because the frequency is dependent on k, and we can have several of them, right? There's nothing that said we had to pick a particular k. So we're going to just sum over all the possibilities. We have this function that's dependent on c1, which is effectively the radial coordinate. And if we look at it in its equation, it has k squared over here and beta, so it's dependent on those two parameters. And then we have the function over here, which is the angular one, and in its equation it only has the one parameter beta, so it's only dependent on beta. And we're simply going to say the full solution is a linear combination of all those, and we're going to work out the details as things come. And just to remind you, the polar coordinates that I mentioned earlier is just c1 equals to ln r and phi equals to c2. And so there we have our picture that the domain that we're solving it on. And so just here is what f is. So we've actually solved the equation for f, even though we don't know what k is explicitly. And so we have f is some constant that's dependent on k cos omega t, where omega also depends on k in the sense that it is ck, and some constant bk times sine omega t. So that's what f is. The initial conditions for this equation we can actually implement by simply looking at what happens if in f we put t equals to 0. So if in f t is equals to 0, sine of omega t vanishes, and cos of omega t is equals to 1. Okay, and so we can use that to fix ak in the following way. Right, so if t is equals to 0, you have psi of xc1 xc2 at time t equals to 0 is equals to this thing. And so what we're effectively going to do is we're going to, because these things, and this is I'm going to show more rigorously later, because these, both of them are solutions to Sturm-Liouville problems, we proved that you can expand any function that obeys the same boundary conditions on this basis, okay, and that is what AK is, okay. The coefficient, the expansion coefficient, is the expansion of the initial condition on that basis, but I'll make it explicit right at the end. And just to comment, the same way you computed the coefficients in our last lecture, in other words, you take the inner product with this of this thing with another with an arbitrary basis function to define AK, you do exactly the same thing to this initial function. So you're given this initial condition, and it corresponds to like the shape of your membrane. So you can imagine if you have your round drum and you put a rock on it, and then it's going to be doing this, and that's your, and then it's standing still. So then your initial condition is basically going to be its shape, and the initial derivative is going to be 0 because it's not moving. If you'd knocked it and it's vibrating, then and you take a picture of it at some point, you know how fast it's moving, then you would be specifying the initial condition as well as the initial derivative in time. Okay, and so you can get the BKs if you know what the initial time derivative is of the surface's motion. And once again, you get this expression simply by substituting, taking the derivative of f with respect to t. Okay, so omegas come out, this becomes sine, and this becomes cos. So the sine term vanishes, and you're left with omega bk times 1 times this expansion. Okay, so you can actually now have a way of determining ak and bk. Okay, so that's at least one thing, and let's now start examining what happens to these other functions. Okay, so these functions are chosen so that they satisfy the boundary conditions and the continuity conditions. So what that basically means is the boundary conditions we're going to have is simply that you have a fixed drum, so your membrane is fixed, is equals to 0 on the rim, okay, and the continuity condition basically becomes, the continuity condition comes that here, because you're in the strange coordinate system, at r equals to 0, you're going to have to say something. And the continuity condition is simply that the function remains smooth over r equals to 0 and is finite. And the other thing you're going to have is that because C2 is an angular variable, so it's equals to 0 here, you go around and it's equals to 2 pi over there, you've got to identify is the solution, you've got to find the solutions that have 0 and 2 pi identified. Okay, so that's what we know about P1 and P2, and we're going to implement that as things happen. And what is interesting is that when you do this, and you actually try and find P1 and P2 that satisfy the boundary conditions as well as the equations, you have Sturm-Liouville problems, and what happens then is you can only solve the problem as we showed for certain of the parameters. So you have certain special parameters, infinite ones of them, but discrete ones coming out, which actually allows you to fix, gives you values for these separation constants, so they're no longer continuous, they're actually discrete. And so the sum is basically non-integral. It's an infinite sum over these parameters. Okay. And when you've fixed beta and k, you've effectively fixed the frequencies. And this is where the beautiful thing comes in. Your geometry of your drum and the ODEs you're solving are actually fixing the vibration frequencies of your drum. Okay, so let's have a look first at the easier one. When I get these problems, I write down these separation equations, and then I always solve the ones I can solve easily first. And that's a good way to go because you actually get a lot of insight from them. So we have P2, C2 over P2 is equals to minus beta. That's just, again, a harmonic equation, okay, which we're going to solve. But before we do that, let's just look at the continuity condition. We have that this thing gets identified as you go around. And so that is that you basically have periodic boundary conditions, which is basically this expression. So basically, P2 of C2, you want to be equals to itself if you've added 2 pi, right? So basically, modulo 2 pi, there should be no difference in your solution. Okay, so now we can go in and write down the general solution for B. It's your harmonic equation, and it has because it's second order, it has 2 independent solutions, and the 2 independent solutions are just a constant times cos times the square root of beta plus a constant times sine times the square root of beta. Okay, so that's just a normal way of solving that, basically the harmonic equation. And so this is the general solution, and we first write down the general solution, and now we're going to actually impose these boundary conditions. And if you impose the boundary conditions, you see that this thing is periodic if and only if when you let C go to C plus 2 pi, the value is the same, and that's only true if beta, the square root of beta is an integer. Okay. So this condition basically chooses the allowed parameters that you have, and in this case, beta takes on values of n squared, where n is basically 0 or a positive integer. Okay, and so now we have written P2, and I'm going to change the way I label it. I'm going to just label it with an integer because that's very natural, to AN cos n C2 BN sine n C2. Okay, and so over here, we can replace that beta also with n, knowing that it's an integer and knowing that the summation is what we would normally expect. Okay, so I'm just going to leave you there. Okay, so now let's just get all those things. So now I've rewritten out the wave equation as the sum over k, which we haven't yet fixed, it's still arbitrary, but it enters into f and the frequency, and we've gotten our first set of basis functions explicitly. It is simply sine and cos with constants in front of it, and what we need to remain to do is solve this equation, and this equation is simply p double prime 1 over c2 times k squared times e to the 2 c1 minus n squared p1 of c1. Okay, where we know c1 goes in this domain, and we're now going to basically start focusing on this equation, because once we've solved this equation, we've effectively, it is also a Sturm-Liouville-like problem, but it is a little bit more complicated. And so I want to actually give you an idea of the techniques that are used to solve it in general. Okay, so the boundary conditions we're going to put on P1 is basically when C1 is equals to minus infinity, which is basically at the 0 point, we want it to be bounded. And we want it on the boundary where P1 or C1 is equals to ln of R1, we want it to be 0. And that's basically the Dirichlet boundary condition that we're specifying what the function is on the boundary. Okay. And the Sturm-Liouville theorem, and you can actually see that this thing, it's not, this one like this is in Sturm-Liouville form. Okay, so the Sturm-Liouville theorem, this is basically a Sturm-Liouville problem, but be careful, it is not n that's the parameter. We give it an n, and k is basically the parameter. Okay, so this e to the 2c is the weighting function, and it's positive, which is the only requirement. And then we have q, which is just the constant, and then the sort of the p that went into the Sturm-Liouville problem over here is just 1. Be very careful with that. Whenever you try and apply the Sturm-Liouville theorem or anything to do with the Sturm-Liouville problem, make sure you've written it in that form that we were dealing with the last time. Otherwise, you make statement that's not true. Okay. And in particular, you make statements that's not true because you get the wrong weighting function in your integrals. Okay, so that's an important thing. Make sure this thing is written in Sturm-Liouville form, and that will be one of your exercises actually to show that you can write any second-order differential equation in the form that we had. And it's just good to know how to do it in general. But fortunately, this guy is. Okay, so the Sturm-Liouville theorem basically says you're going to have an ordered set of values of k that are discrete, that start at 0 and go to infinity. They're going to be increasing in all those properties we had in the last time. And the moment you have k, you have a frequency associated with k. So this equation then tells you something else, right? You're going to have the situation where you're going to have a basis function that goes round, that fixes n. You choose an n. Okay, and here you can see it. If you have no nodes as you go round, and by nodes I mean places where P2 equals to 0, then n is equals to 0. So there you have that case. Over here, you basically, as you're going round, you go from a 0, you basically have 2 zeros, right? You have 1. You basically have a 0 on the axis. So as you go round, you have a 0. So that's another, this is more. Okay, these are the cos, sorry. So here, if you look at this expansion, you can have even and odd functions. So the odd functions are referred to the sign if you have bn non-zero, and the even functions refer to a cos if you have an non-zero. So here you have odd, so you have sine you have n equals to 1, then you can see you have a 0 over here. When phi is equals to 0, you go around, and when phi is equals to pi, you're again 0. And then over here, you have the case where you have an even function, so n is equals to 1, and you're positive on you can be positive on the x-axis over here, you go around to 2 pi, then you have a 0, and then you go around again, and you have another 0 at a pi over 3 over 2 pi over there. Okay, so that's an even function, and you can now see that if n goes up, then you can have the situation where you can have this case, right? If n is equals to 2 and you have an even function, cos is positive on the x-axis, you go up. At pi over 4, you have a 0, because 2 times pi over 4 will give you pi over 2, and cos of that is 0. You go past, and then you're going to have another 0 when you get over here, and you're going to go on. So the number n actually gives you the number of nodes in your solution. Okay, and here is a similar thing, right? Over here you have once again an odd function with n equals to 3, and you can count your zeros. The top, in the upper half plane, you have the 3 zeros over there. Okay, so there's a very distinct, at least in the angular, but in both of them actually, there's a very distinct relationship between which function you actually have here and what the angular part looks like. Okay, and what is also interesting, once for a given n, you now go to the second function, and this function is basically giving you nodes that go out. So the first thing is this one, if you have no nodes that go out, you have a drum mode that goes just basically up and down and up and down, and it's just 0 at the bottom. Okay, and that node's frequency, they call the fundamental frequency on your drum, and it is basically fixed by the fact that n is equals to 0 over here, right? And so you put n equals to 0 in this equation, and then you find the lowest solution of k. In other words, the one that basically shoots from the boundary to the middle and is continuous. And that, the k that gives you that, if you multiply it by c, that'll actually fix the frequency of your drum. Okay, so your geometry fixes which frequencies is possible. It's true for any object. If you had a square, and that's actually a problem you're going to do in the problem set, you're going to compare it, and it's a very easy problem to solve, but you can get the frequencies out. And it turns out those frequencies are very close to the things that look corresponding to the corresponding pictures in the circles. They change, but they're very, very close. So if you wanted a first estimate, especially for the higher ones, then you would just solve the square. And that's actually what I wanted to see why I did the ellipse. I wanted to see how these frequencies would change if you change the shape of your drum. And the actual answer is they change, but they change very slowly. And a very good guess for the first ones are basically the ones of the round drum. Okay. So that just gives you an idea of how these frequencies are done. Okay, so you're going to have, for an n and a k, you're going to have a different shape of your drum, and that pattern is going to vibrate with a different frequency. So when you look at drummers, they have different ways of where they hit the drum, okay, and especially Indian drummers. And what they're doing when they're doing that, they are exciting different modes, and then this drum sounds differently because the frequencies of the mode are different. So if you were to hit the drum in the middle, you would be more likely to excite the fundamental mode, so the lowest mode of the drum. If you hit the drum, say, with this mode, you hit it like in the middle, where you have the two sticks, then you're going to be exciting a mode like that. Actually, no, you have a choice. If you hit them together, you're going to excite the mode like this. If you hit them separately, you can have modes that oscillate like this. And every one, the way you choose, or every mode, if you hit it in a way in which the geometry in which you hit it corresponds to the mode, then you are most likely to excite that frequency. So drumming is a skill, but it's also a scientific skill. And then you can also see like the Indian drum that has those round circles on it. That's basically helping you to excite a very, very high frequency mode, because it sort of made the drum slightly stiff, the membrane of the drum slightly stiff. So you're not solving exactly that problem anymore. You're solving a membrane that's not uniform, but that allows you to just pick one of those things preferentially. There's other techniques as well. I mean, most drums you just hit with the sticks, and then you're just exciting up and down. But there are ways in which you can like hit the surface of the drum. And what you do then is you actually start a wave that's a combination of those that moves to the side, bounces back, and comes back at you. And then you have a different set of frequencies that's actually a combination of those fundamental frequencies. So it's true for absolutely any object. Like any object has natural frequencies. And so just one thing is that there's this problem that if you have an object like this and you have its and you can always find its natural frequencies, it's likely to absorb energy if you push it at the same frequency as that natural frequency. So when you have your drum technique, the rhythm with which you hit it is also got to be close to the actual frequency of the drum. Because what happens, suppose you hit it once, then you excite the mode to go down and come up. If you hit it too soon again, then you're basically going to kill it. But if you hit it at just the right time, you're going to amplify it further. So this amplification happens in all engineering structures. So there's bridges. Whenever, let's give you a local example. When they designed the SKA dishes, right, you have like a cup like this. They get the engineering, they get the shape of the dish, and then they can't solve it with separation of variables. They put it into an engineering package that actually gets an estimate of what these natural modes of the thing are and what frequencies the structure is going to vibrate at. And the reason they want that is they want to engineer it so that that frequency is very different from all the frequency it's going to encounter. Because the moment you have a frequency, the moment you give energy in a frequency that's close to its natural frequency, it just goes, absorbs it, and the thing shakes to pieces. And the only way that the telescope can get energy is if you have wind blowing over it, and then it can push it. And if that frequency that it shudders is the same as what the wind is, or the wind that's pushing it, then your telescope can like break apart. Another example of frequencies, and all that basically chemistry and quantum mechanics is if you look at the hydrogen atom, you're going to be solving Helmholtz's equation as well as we derived in lecture 21. You're just going to have a different time part. And the interesting thing is the frequency you get out of Helmholtz's equation determine the energy levels and determine the light interactions. So if you are to shine a laser at a group of atoms, okay, normally the light will just go through, except if you shine the laser at the exact frequency that the atom is bound, like the springs in the atom are bound. If you tune the laser to that, you're going to make the atom vibrate more and more and more and more and more, and then the thing is going to pull up, the electrons or the other atoms are going to pull apart because you've put energy in there. And another South African example that's no longer there, they used this technique to try and separate uranium. So how they used it is the uranium you can combine with fluorine. You can have an atom that is, they call it UF6. So you basically have your uranium atom, and then you have like 6 bonds with fluorine around it. And so you can imagine your heavy uranium atom, very light, 6 light atoms that are connected basically symmetrically with springs. And so these things oscillate at a certain frequency, and what determines that frequency is actually the weight of the uranium atom. And so you have two isotopes of uranium now. The one is heavier than the other one. So the thing that's determining the spring frequency is the weight. So the heavier atom is going to vibrate slightly differently from the lighter one. And so the technique was you shoot in a laser that is so finely tuned that it picks the frequency, say, of the heavier one in the gas. It makes the heavier one vibrate completely and lose one of its fluorine atoms, so it's an ionized. You put an electric field on and you suck out all the heavier one and you leave the other one behind. And you just do this repeatedly to try and choose the one molecule out of the other one. Okay. It has a lot of applications if you have the control of the fundamental frequencies and the normal modes of your problem. Right, but now I've showed you nice pictures, and I have not yet told you how to solve the second one, okay? And you've got to be able to solve the second one to actually get the frequencies out. And so I'm going to now start doing that. And it's also going to be a bit of an example of the Sturm-Liouville theory and all the techniques that you can use to solve it. And I'm going to basically take a more general picture, then follow and tell you how, if I were to be nowhere, right? If I didn't follow, it just gives you the answer. If I didn't have that thing and I saw just that equation, what would I do? Okay, so, just one further comment before I go on. So this picture actually comes from a journal article that worked out the membranes on a circle and on an ellipse. And just the citation, if you do homework and you give me a citation, you must please make it such that when you go back again and look at it, you can find it. So just telling me you got it off the web somewhere is not going to work. You actually need to write down either the web address or just so that you can afterwards, if you wanted to look at it again, go back and find it. Okay. For most of the time, I'm not going to go and check it, but just for future reference, it's to keep track of information rather than, and to give credit. And typically, this is how you would do it if you were writing a research article. Another comment before I go on, and this goes with, suppose I get a random equation like this, and I now want to solve it. I know its properties, it's a Sturm-Liouville equation I can write in the form, but solving it is sometimes quite tricky. So I'm going to give you some of the tools. They call it the Digital Library of Mathematical Functions. It used to be a thick book called Abramovich and Steigen. Okay, that's in the library, you get a book like that. It's actually nice to take out once and look through. What this book does is it basically takes all the classical Sturm-Liouville problems that have arisen and people have studied for various reasons, gives all their properties, and for the old school people before computers, gives sort of tables of all the frequencies that or the zeros that arise in these functions and how they behave and some of the other properties. It's no longer a book. It's now an online resource. It's totally free. It's called the Digital Library of Mathematical Functions. And it is held at NIST. So NIST is a governmental organization, a research organization in the United States. And so I actually encourage you to go and poke around there. It gives you integrals, and mainly it gives you these functions and a lot of their properties, because the functions that obey these Sturm-Liouville equations are amazingly rich. You're going to see some of the properties when I look at Bessel, but people have played with them a lot because they appear so many places. Almost always, if you solve Helmholtz equation, whenever you solve Helmholtz equation on a disk, you get this equation, okay? The other equations in 3 dimensions that you also solve, and you get a similar equation like this. And so all the properties are actually labeled there, and you'll get similar pictures as these, and you'll also get zeros that I'll show you later. You can also find them there. Okay, so the first thing I do that you can do, or various things that you can do if you get an equation like this, is the thing you can do is change variables, and then you can make the equation look different and hope you can solve that one. And the reason that I'm going to change variables now, the problem, of course, is what change of variables do you want to choose? Okay, so there are various ways of motivating. Maybe one, you want to choose something that it makes it easier for you to impose the boundary conditions, or is more natural. And so the natural change of variables that suggests itself here is simply to change variables so that instead of using this funny thing C, you use the radial coordinate or the polar coordinate. The advantage of that is when you do that, you actually get a polynomial equation which makes it possible to solve it. Okay. Historically, also, when I think they went directly to polar coordinates rather than the route that we did with the general way of separating constants. And so the Bessel, who actually looked at this equation well, thoroughly, and possibly first, he was actually working in polar coordinates. Okay, but different coordinates give you different pictures of what this equation actually does. So let's do the first thing, change variables. I'm going to let C1 equals to ln r, so I'm going to go to the polar variables. And then derivatives with respect to C1 is then just equals to r times the derivative with respect to r. Okay, and I'm going to now use that and to rewrite this whole equation in terms of r. And so we're going to have d dx C1, which is basically r times ddr, applied to d dx C1, which is just r times ddr of P1. And I've renamed the P1 because it's no longer viewed as a function of C1, but rather of r. Okay, so just to avoid confusion. And then here I've replaced the e to the 2 C1 by r squared minus n squared P1 of r. Okay, so that equation is Bessel's equation. Okay, this one, just be careful here, this one is actually not in Sturm-Liouville form. Okay, what do you have to do to get it to Sturm-Liouville form? Right, you have to take away this r, because the Sturm-Liouville form is basically ddr times p of r times ddr of the function, plus some weighting function which is positive times the parameter plus some other, plus or minus some other function. Okay, so to get it to Sturm-Liouville form, you have to divide by r in these coordinates. So this is also the trick. Over here it is in Sturm-Liouville form. So just be careful that whenever you eventually get to talking about anything related to the Sturm-Liouville problem or applying its theorems, make sure you're in the right form. Okay, so the boundary conditions also have to be transformed. So P1 at 0 now, when C is minus infinity, has to be bounded, so it's got to be less than infinity. And P1 at R1 must be equals to 0. Okay, so now I've just rewritten it like this. Sorry, I had a set of notes that did this nicely, and it was in X and Y, and I was gonna make too many mistakes when I quickly changed it. So instead of, I've now replaced the P1 tilde with a Y, so that's my function, dependent variable, and I've placed the R with an X, okay? And so the function, and I've divided through by the X so that we're in Sturm-Liouville form. So I'm looking at solving this equation in general. And I'm actually not going to be able to finish this time. But I'm going to basically give you all the techniques that I know how to solve it, and there's several of them, and some of the other properties. And then I'm going to look at the actual frequencies that are possible on the drum and how you compute them. So I'm basically going to start and then look at all the solutions to that problem, and then actually look at their properties and comment what I would do as I go along. So the first thing I do is when I have a problem like this, I look at all the special cases, okay? You basically choose the parameters lambda and alpha so that you can solve the equation easily, just as a first guess. And over here, I'm not at least going to start by assuming that alpha is an integer, because you can actually solve this equation when alpha is not an integer. And this equation is also, it's still Bessel's equation, but that equation often appears in 3 dimensions and in quantum mechanics. So that's why I'm just going to leave it general for now. Okay, so the first one, let's look at all possible solutions. If we set lambda equals to 0, okay, so we just put one of the parameters equals to 0, then we have an equation that looks like this. And whenever you have an equation that looks like this, where you have the dependent variable multiplying y double prime, in other words, you take 2 derivatives with respect to x, and you're multiplying with x squared. And the same here, you take 1 derivative with respect to x, and you multiply with x, and here this is just a constant. Whenever you have something like that, you can suspect that y is a function of, is x to the power something. Okay, because what you're doing is you're taking derivatives and then you're fixing them. So if you just had x to the n, you could assume that the solution was in that form, put it in and find out what n, or n is a bad choice. Beta, you could put it in and find out what that thing is. And it's one of the techniques I think you learned in the second year. Okay. So let's look, even though this is simple, let's make it even simpler just to get yourself warmed up. If alpha is equals to 0, right, then you can rewrite this equation like y double prime over y prime is equals to minus 1 over x. Okay, very simplest case, that simply means that the ln of y prime is equals to the minus the ln x plus c, or that y prime is equals to d over x. And so you have y equals to d times ln x plus e. Okay, possibility 1. So it's actually the example where you can't make it a power series expansion. So that's why it's actually important, before you make any assumption, go through, write down what you're assuming before you make an ansatz. Okay, so if alpha is 0, we now have the general solution. It is the general solution because it's a second order equation, therefore you're going to have 2 independent solutions. 2 independent constants must always appear. Okay, if alpha is greater than 0, which basically includes the n, all the n's that we have, we can then make this assumption that y equals to x to the b and work out the consequences. And the reason we do that, or the reason we made it in the first place, is this property that you have the powers that x is raised to is comparable to the number of derivatives. So you make that assumption, you substitute it into this equation, and what you then get is, if you basically take y is equals to x to the b, you take 2 derivatives. Okay, so you have beta times beta minus 1, x to the beta minus 2 times x to the 2, so that's just x to the beta. Okay, and I've dropped x to the beta. Over here you have 1 derivative of respect to y, so you just have beta times x to the beta minus 1 times x, so it's just beta times x to the beta, and I drop x to the beta, minus x to the beta, so you just have alpha squared. So you then, if you substitute this ansatz into that equation, you basically get this condition. Oops. And so if you simplify this thing, you see that the beta goes off here, and you basically have beta squared is equals to alpha squared, and then you have beta is equals to plus minus alpha. Okay, so the general solution, if lambda is equals to 0 and alpha is greater than 0, is, sorry, there's a mistake. That should be x. Okay. X to the alpha is C1 x to the alpha and C2x to the minus alpha. Okay, so now we've already learned something. If we're going to guess, we can guess a solution based on the structure of the equations. And this is actually why I made the transformation to the R variable more than what I wanted to have it intuitively associated with the boundaries, is because I could actually get the structure where it was easy for me to guess the answer. Okay, so when lambda is not equals to 0, in fact, we're going to do when lambda is equals to 1. Okay, the reason, and that's going to be general enough to include all the possibilities, and I'll show that explicitly later on, because you can always rescale your variable x and or your function y so that you set lambda equals to 1. Okay, so if you can solve the problem where lambda is equals to 1, you can reverse the process and find the solution for lambda equals to anything. Okay, but first we're going to simply start solving the problem of lambda equals to 1. Okay, so if lambda equals to 1, you're basically trying to solve this equation. Okay, the one thing I must say is note, when we're writing these things down over here, we've forgotten that we haven't used the boundary conditions, right? The boundary conditions would fix C1 and C2. We've been finding the general solution. And this is what actually makes Bessel's equation nice, is because you can find this the general solution, get a lot of properties, and put the boundary conditions in afterwards. What happened with the other example is you couldn't do that, and then you had to work very hard. But anyway, so we have lambda is equals to 1, so we're trying to solve this equation. And the way we're going to do it is use what we call Frobenius method. It's basically a generalization of this ansatz. And so how it works, something's very weird with my formatting, is we're basically going to assume you have, so I'm basically going to call the equation where lambda is equals to 1 in B, BB. We're going to assume the solutions have a series expansion, and that the series expansion is going to have the following form. You're going to have some factor x to the beta that you can either take out that's not dependent on what you're summing over, and then you're going to have a whole combination of various powers of x. So you're basically making a power series of expansion where m is an integer and beta is possibly not. It doesn't have to be. It turns out to be in the cases that we're going to look at for this problem, but in general in quantum mechanics it's often a half. Okay, so, and what we're going to do is we're going to take this thing and we're going to substitute it in to this expression, and we're going to try and from that determine what AM and beta is. And so let's just do it. To be able to do it, we're going to need the derivative of y of alpha to the x. Okay, so the first derivative is just basically the derivative of x, so it's m plus beta times that thing minus 1 over there. And this other derivative we're going to need is y second derivative, so that's just the derivative of this thing, so it is m plus b times that guy times there times that to the minus 2. And now we substitute these two into that expression, but it's convenient to just write it out first. Okay, so we're basically going to substitute these two expressions in here, where this thing is simply not in Sturm-Liouville form. It's simply expanded, and I've multiplied through by x, so that once again, I have the same structure as what I had in my special case. So that's why it's so useful if you're starting from nothing. Look at the special cases, because they often give you clues of how to do the general case, and in fact how you want to write your equation in a way that the general solution can be found, right? So if you started from your special cases and you saw, oh, this ansatz works already over here, it is likely that a generalized ansatz is going to work in this case. Okay, so this choice of solving it this way using Frobenius method was basically a generalization of a special case that he saw. Okay, so let's do it now. So here is this first term. Okay, so the first term is just y double prime that comes from there times am times x to the m plus beta minus 2. Okay, multiplied by x squared, so it comes back in here. Plus, let's go back. X times y prime, so that's your y prime is your m plus beta times am, m plus beta minus 1 times x, which is over there, minus alpha squared times am times x to the m plus beta. Okay, and here comes the tricky term. The x squared multiplied by y gives you a plus 2 over here. Okay, so you now have the summation over m goes to 0 to infinity, and it would have been very, very convenient if that plus 2 wasn't there, because then you could just group all the terms together, forget about the x to the m, and say they must all be 0 independently. But you can't do that, because you have to compare like powers. So the way you get rid of this thing is you can see that this is just a summation over m, so you can relabel m. And so we do that. So the first part is just, so these parts, everything that is am x to the m plus beta, I've now grouped together. Okay, so there's the m plus beta squared, minus m plus beta, plus m plus beta, so they cancel, minus alpha squared. Okay, so all these terms over there, I've gone and I've put in that first term. Now, this one, I want to change so that it looks similar to this thing. And the way I change it is I give the index a new label. Okay, so I'm going to say this last term, summed over m starting at 0, I can actually say, let me have a new index m hat, so that beta plus m hat is equals to, removes this 2 up here. So I'm going to say m hat is simply m plus 2. Okay, so if I do that, I change my summation index. So then the things that you have to be careful about is firstly the boundary term where you start. So m hat is m plus 2. So if m is 0, m hat is 2. And then you simply replace m with its expression in terms of m hat. So m hat equals m plus 2, so m equals m hat minus 2. And x equals to m hat, and then you have x to the power m plus 2, which is just m hat plus beta. And now you can write this thing out together. I think that's all I've got. Except, so now what you can do is you can set the coefficients of the things in front of like powers of m to 0. Okay, because that's the only way it's going to happen, because it's got to be true for any x. And what that gives you is a relationship between these coefficients in front here and beta that you can actually solve to get the explicit values for am. Okay. That's all I have slides for at the moment, and it's also getting quite late. So I think I'm actually going to not do it. I'll rather make it properly and put it on the slides for you for next time. But it just gives you a general idea. I'm basically just going to start from the series and go on and look at some of the other properties. Have you seen this technique before? Okay, so you're comfortable with it. Cool. Well, this is a reminder, because you can get fit, because you're going to get a couple of examples like that. But anyway, so next time I'll start looking at basically you get recursion relationships here. And I'll start looking at how you go from the recursion relationships to the actual functions. But before I do that, I just want to end so you can sort of get back to the picture of we're getting the solution system or problem with the nodes that come in. I want to give you a graphical picture of what the functions actually look like. And here they are. Okay, so the Bessel functions are of a specific kind. Okay, the ones that are finite at the boundary have this property. They basically have a maximum amplitude at the boundary. They are oscillatory in the sense that they have, you can specify any number of zeros. They're not periodic in the sense that the zeros are uniformly distributed. And so you can actually see that one has a large mode, the mode that goes like this. The first one is basically you start there and you go to that's now on the boundary, and that's the mode that goes in. And so you can see that these functions sort of intuitively capture what you would expect from the drum, right? That because far away from the boundary, the amplitude is bigger than close to the boundary. And they come from the functions themselves. And the places at which these zeros actually occur actually set the frequencies. And so I'll tell you more about the Bessel functions and how they actually plotted this and some of the other properties next time. But I just wanted to give you a feel for what was actually used to make those plots, where you actually, now you can see that there was nodes that went round like that on the drum head and nodes that went in. And the nodes that go in are dominated by that. So their spacing is different. In other words, they're more concentrated near the edge, and then there's a bigger and bigger motion near the center. Okay, so I'm going to stop there lecture-wise, and then next time